Welcome to lesson 5.1, derivatives of exponential functions and other exponential functions. We're going to start on page 4, and we're taking the derivative of a new function, 2 to the x. Now notice it's not the power rule, because it's not x to the power 2, it's 2 to the power x. So if the exponent is up here, we need a new rule. So we're going to go back to the definition of derivative. F prime of x is equal to the limit as h goes to 0, f of x plus h minus f of x all over h. Instantaneous rate of change, slope as the change in x goes to 0. And that's going to be the limit as h goes to 0, 2 to the x plus h minus 2 to the x all over h. Now I see this adding exponents here. Well, why would I be adding exponents? Because I'm multiplying. So let's separate that out. Let's rewrite that as 2 to the x times 2 to the h, because the rule for that is you add the exponents and get the one before. And now I can factor the top. I can factor out 2 to the x, and 2 to the x doesn't have h in it. So I'll do it twice, but I could factor this out. I could factor 2 to the x out. But since it doesn't have h in it, I could just let h go to 0 by itself and say this is 2 to the x times the limit as h goes to 0, 2 to the h minus 1 over h, and that's f primed. So the derivative of f primed, the derivative of f, the derivative of 2 to the x is 2 to the x times something, times this. Well, h can't be 0 because you can't put 0 on the bottom of a fraction. But if you put 0 into the top, you get 2 to the 0 is 1, 1 minus 1. This is 0 over 0. So it might have a limit that exists. It might have a hole. It might have a y value with a hole, and the hole is at h equals 0, and it does. If you go to your calculator and you type this in, and you let h be 0.001, I'm going to pick something very close to 0, and I get the derivative of 2 to the x is 2 to the x times 0.69, roughly. Okay, so the derivative of 2 to the x is 2 to the x times 0.69. So what does that mean? Well, if I drew 2 to the x, there's 2 to the x, y-intercept is 1, and it doubles every time. There's y equals 2 to the x. I'm going to call that f. So f primed is the same graph, but times 0.69. So times 0.69 is a vertical compression. So if I draw f primed, it's the same shape, but compressed. So let me show you over here on Desmos. The red one is the graph of 2 to the x. Look, I'm graphing b to the x, where b is 2. And the green one is f primed. So it's the red one with a vertical compression. So it's slightly lower than 2 to the x. Okay. Let's do the same for 3 to the x. The derivative of 3 to the x, well, let me skip the first step and go, it's the limit as h goes to 0, 3 to the x plus h minus 3 to the x all over h. I can skip all these steps because they all happen exactly the same way, except the bases are 3 instead of 2. I can skip to the very last step. This is 3 to the x times the limit as h goes to 0, 3 to the h minus 1 over h. And, again, take this number, make h equals 0.01, and you're going to get 3 to the x times 1.1, roughly. Well, what does that mean? Well, if you draw the graph of 3 to the x, its derivative is the same, but it's got a vertical stretch on it, a very small vertical stretch. So there's f. It grows a little faster than 2 to the x, and f primed is very slightly above it. And we'll go look at Desmos too. Okay, whoops. Come on. There. All right, almost exactly the same graph, but slightly different. Last one, 10 to the x, and I hope you can see where this is going, sort of. F prime of x is, I'll just write out the last step here. And that's, if you plug in h is very close to 0, you get something like 2.3. So 10 to the x grows very fast because the base is big. And its derivative is more than double f. So the question then is, what if this limit was 1? If that limit was 1, then you would have a graph, a function that was its own derivative. If this limit was 1, then the derivative of 2 to the x would be 2 to the x times 1, and it would be the same. So we define a number e. We define a number e, find the button on your calculator, so that the derivative of e to the x is e to the x. We take this limit, and we say this number here is going to be 1. So the derivative of e to the x is e to the x. It's between 2 and 3, it's closer to 3, and here's the curve, e to the x. When the y value is 1, the slope is 1. These low positive y values have low positive slopes, and as the slope goes up, the y value goes up, and as the y value goes up, the slope goes up. The slope at every point is the same as the y value. So we develop this new number. The derivative of e to the x is e to the x. And if you look on Desmos here, I'm not going to hit it exactly, but it's around 2.8. It's around 2.7. And that's the base that makes the exponential function and its derivative the same. So the point of e to the x is that the derivative of e to the x is e to the x. I'll join you on the next page to see what we do with it.